Hello, guys. I hope you hear me. As she introduced me, I have a lot of experience in software development. About a year ago, a year and a half, I decided to learn Rust, and I've tried actually several times before that, and it wasn't successful because I didn't have a proper project. And what changed is we released an open API spec for the biggest of the VMware APIs. So that's the virtual infrastructure API, how you manage your data center essentially. And it's a huge API, but we had an open API spec, and so I decided, okay, it's going to take me a couple of weeks maybe to do in Rust, and I learned Rust. And it took me a little bit longer, and you'll see why. And I hope it's a useful talk to you because I mean, this is an API that was designed with Java, C++, XML technologies, and we will be facing those for a number of years ahead. I mean, there's still a lot of Java and C++ developers around. They're building new systems even, and they don't fit naturally into the Rust ecosystem. So we have to have some ways to deal with those systems when we encounter them. Okay. So first, I want to show you a demo, so to say my library works for interfacing the API. And what you see is a Ratatouille-based application in Rust that you can browse your virtual inventory, and you receive kind of live updates from the underlying system through the API. You can open different objects, you can open different inventories, navigate collections, that sort of thing. And it was a pleasure to actually write one once I got the API correctly exposed into Rust. Okay, so the talk, the way I'm going to structure it is around this 6-in-1 joke. So you'll see some graphics and the titles as well. But essentially, we're going to talk about the problem, the API that we have to interface. Then we will see what it actually means to expose it properly in Rust. So what is the developer experience we want? And I'll talk about a couple failed attempts I did at tackling the problem. And then I finally will talk about the solution that actually solved, or the solution I selected. It might not be the right one. I'll appreciate even feedback because some of you, or many of you, know Rust better than I. And lastly, I want to also share a little bit of a success story for me with Rust macros. So they helped me solve somewhat complicated for me challenge. There is the examples that I will show. I'll show quite a bit of code. You can find them in a kind of compilable form on this address. Okay. So how big of a problem we're talking about? So the kind of vCenter, this virtual infrastructure API, started in the early 2000s, and it was based on the SOAP technology. It was implemented in C++, and that's how it worked for a number of years. And we've been adding stuff to it to handle different things. So, for example, if you look at PCI pass-through devices, so how you get things like SmartNICs or GPUs into the API, there are like 6 different ways these things are exposed. So there is a lot of stuff in there. It kind of totals over 2,000 APIs. There is over 2,000 distinct data structures, a lot of enumerated types. For every structure, we also have like an array type. So you have maybe a virtual device, and then you have an array of virtual devices. So we have to have these 2 types in order to define the XML or the JSON kind of schemas. A complication that comes with that era of technology, the C++ and XML, is inheritance. So this is really where the challenge was laid for me, how to fit that in Rust, because there is no natural mapping of this inheritance construct from C++ to Rust. And specifically, when the inheritance is like deep, like 6-7 levels deep. So we don't have that in Rust and Go, and modern kind of things like if you look at proto buffers for APIs, they just don't have that. So then the last challenge I had is we have something like SQL. We saw SQL actually in the last talk. And if you've ever dealt with SQL and with some strongly typed language like Rust, the answers you get from a SQL query are a bit unwieldy. They require a lot of type checks, a lot of like, is this optional thing there? What is the actual type that I got back from the database? It's a lot of boilerplate code. And so that was an additional challenge because we have such an API as well. Okay, so first about the inheritance. For those of you that haven't been exposed to Java or C++ or XML for that matter, basically for 30 years, software developers used to model the world as hierarchies. Anytime there was an alternative, like I can have an Ethernet card or I can have a virtual disk, what I'll do is I define a base type, and then from that base type, I define children that specialize it in different ways. Maybe it started with biology. This is how we classified animals. Maybe Darwin kind of said this design principle of object-oriented modeling. But yeah, this is what we used for 30 years in programming. And these hierarchies, if you look at Java, .NET, they usually go very deep. So they go many levels. And this just doesn't fit in Rust. And to map it in Rust, we want to get some functionality. So in this case, we're looking only at data. If you look at Java or .NET, C++, you also have behaviors. So luckily, in the case of an API that gives you back data, you compose data structures, you only have half of the problem to deal with. And this is how you manage the inheritance between data structures. And what we want to have is kind of infallible assignment. So say we have something specific like a lion, and we want to put it in a container for animals, okay? So we should have an infallible way to convert the lion to an animal reference and then put it in the container for animals. We should be able to test. So say we get a reference to an animal, maybe from a container, and we want to be able to test what type of animal is that. We want to be able to also, in a fallible way, cast, so downcast, like from animal up down to the lion. We want to be able to say, hey, convert this animal to a lion, and it should return maybe an option, so whether it's successful or not. Yeah. We want to be able to also have containers like vectors in the virtual infrastructure API. This is the only kind of container I had to deal with. And we want to be able to say I have a reference to an animal. I want to be able through that reference to access the functionality of the animal type. Even though it might be some more specific. It might be a mammal, it could be a carnivore, so it has more properties, but I want to be able to see the properties through the animal reference. So when I get results from the API, I can make some inference about it from the base types. And lastly, we want to have some serialization and deserialization in JSON in this case. So Rust doesn't have these out of the box, and I had to come up with some solutions. So I started learning Rust. I read the book, most of it, so enough to feel kind of comfortable writing code. And I started thinking how I'm going to project the API. I couldn't figure out a really obvious way. I went to rust.org. There is a nice forum there. I asked, okay, what do I do? And the guy said, hey, we have enums in Rust, and they're fantastic for this use case. And so I said, and I thought, how am I going to use the enums? And you can make a tree structure with the enums. So you can nest enums. If you have like 6, 7 levels of inheritance, you can do such nesting. So you have it here. And yeah, that worked. Actually, SERDI, the serialization crate that many of you have probably seen, it works out of the box. You can do these complex kind of enums. You can annotate them properly. What is a discriminator? What is the values for each type that it has to unmarshal? And it works very well even with these like multiple levels of nesting. The thing is that the developer experience was awful. So I could work around some of that through basically providing some utility functions. So say I want to upcast a lion to an animal, and that will mean wrapping the lion struct into multiple enums to get an animal. So you can do that maybe with these to, from, try to, try from. for the reverse, for the downcast. But that's a lot of boilerplate that I had to generate. And still, I mean, the experience I was getting as trying to write some small programs wasn't very good. So that's kind of, I discarded this path. Although it is workable, and maybe for a smaller API, maybe a few hundred types, a couple, 2-3 levels of inheritance, it would work. But if you have 6-7 levels, it was just not good. Okay, so next try, I thought, okay, Rust is a low-level language. It's much like C. So you can maybe have a pointer to a lion, and if I do the memory layout correctly, then I can cast the pointer. So it doesn't. So now the Rust thinks it's an animal, and I can treat it as an animal. But then I need to get back. So I need to add some metadata, and I added this struct type that you see. And I had to make it public because the default thing doesn't work with private fields. It only works with public fields. And so it started becoming very messy. And also, when I do these unsafe casts of the pointers, that might mess up things, right? It may mess up my memory if Rust decides to move something. Yeah. So it thinks it's maybe an animal, moves a little bit of data, but it was a lion, so there was actually more data. I didn't know. I think the transmute is documented that you have to transmute only between kind of equally sized objects. So yeah, I kind of abandoned that for the safety, and also like this public struct type wasn't nice. Like people can mess with it, and yeah, so that wasn't good. So even at the beginning of my journey, I saw the traits, and this is where the solution was for me. I think we saw that example yesterday in Jacob Pratt's presentation. So that's kind of interesting. I have the same example here with animal and dog. But basically, if you have traits for the base types, for the types that are polymorphic, this allows you to do the infallible conversion very easy. So I can get a dog, and I can just pass it to a function that requires an animal. Or I can put it in a container that wants an animal, or a field that wants an animal. So that works very easy. It kind of a little bit reminds of how Java and C++ work. To access the data from the base types, I could implement accessor methods in the traits. Yeah, and these traits, yeah, the fat pointer, you probably know how it works, but yeah, in Rust, basically, when you pass the din traits, you have 2 pointers. One is to the method table, so you get the proper method table for a dog, but you also get the dog data, but you can treat it as if it's an animal trait, any animal trait in your code. Okay, so here is the use cases that we laid out in the beginning. So yeah, the assignment from a dog to an animal works always, and is infallible. You can access the fields. I said that. I added to the types disassignable from functionality. It wasn't very hard to generate, and it allowed me to do the type testing that we wanted to have. I had to build my own kind of traits to do the type conversion. So I have this into ref and also into box constructs to convert between traits. So in Rust is not working out of the box. If you have an animal trait, you want to go to the mammal trait. It's just it doesn't work. Neither upcasting nor downcasting of traits works. It's a little bit more complicated, so you have to write some code of your own. Yeah, the containers, they work very well, but you have to use boxes because they're different size in memory. The different objects that, so yeah, all the descendant objects, they're typically a little bit bigger. than the parent. Okay, so this is how the trait casting work. I thought this might be interesting, so just showing it. It's a three-step process, I guess. So you first need to get to the any type. And for this, I have like a base trait that I implement for every type I have. So I can convert it to any. That's the standard trust any. Then you downcast it to the specific type, like a dog or a cat. And then this weird quirky syntax with the sum and the question mark actually makes the conversion from a dog or a cat to the specific trait we want as output, in this case, the animal trait. Yeah, and the cases in the match statement are all the valid kind of conversions. So I have those generated as I process the API. Okay, and this was functionally very good. I could write some code, and it looks nice. It looks clean. So this was definitely the solution using traits, much better than the other two options. But it was awfully slow to build. And yeah, I didn't know why is that. I tried to look at the logs of the compiler. There is some tools you can use to profile your builds. And they just told me there is a lot of things you're doing, and that's why. They didn't give me much information beyond that. So I started kind of guessing what is taking up a lot of time. And turned out macros take a lot of time. So if you're ever kind of processing some API and you maybe starting with an open API spec or an XSD or something like that, and you want to build your bindings, don't generate macros. Just generate the code that the macros, the derive macros, are supposed to generate. It's just that the macros, I mean, they're not terribly slow in the usual case, but when you put them into thousands of instances, they do take considerable amount of time. And if I do just the code generation part, that takes like a second or something. So it was kind of no-brainer to do that. Specifically type tag. Type tag is the magic kind of upgrades SERDI to allow it to do the trait serialization and deserialization. So SERDI cannot manage the traits on its own. You have to have this additional trait type tag. That's quite magical, but it works. But still, you know, I removed the derive things, and still it wasn't 20 minutes, it was 10 minutes on the compilation time. So I had to do some further magic. So for serialization and deserialization, when you have these object hierarchies, if you look at Java, there is like an object, which is the root of everything, and that's kind of common, I think, modeling principle that people follow. So they'll have like a root object, and everything will descend from it. And that makes the model very, very highly interconnected. So you cannot kind of prune the graph, because sometimes you will refer to this root object. And when it's the root object, it can be any object in the system. So it is possible then to use maybe only one function for serialization and deserialization when polymorphism is required. So when you have some polymorphic type, you can use these like two functions instead of having like maybe in my case 500 functions for the 500 traits that I had. So they all currently kind of delegate to one. Now the serializer and the deserializer, they go in one place. And there were two huge hierarchies that were kind of purely read-only. So one is the errors, and the other is the events. I kind of flattened them. I decided I'm going to emit only the root types. Like in this case, you see the method fault, which is the error. So it has a cause and it has a message. And this is what many people only care about, like, you know, what is really the message part, or if they have to dig down into the cause. You can read the actual type that came on the wire. So this is like the discriminator that you see in the JSON. in the type field, and with Serde what I could do is kind of marshal all the data that is additional into this extra fields map. So if you are interested into some specific type of error and some specific field, you can still access it. But the compilation time is shrunk a lot because I have a little bit of this dynamic trick here. And similar, we have event structure. So these were like maybe 1,000 data types that or more that were squashed kind of into two. And this reduced like these optimizations overall. They drove me from 20 minutes down to 2 minutes, from maybe 100 megabyte executable down to 20 megabyte executables. So that was kind of good. The last thing I wanted to talk about is just the macros. So we have a kind of query API, so similar to SQL. So you give it property paths, the kind of you see there with the summary, overall status, runtime connection state, name. So these are paths into the host system object, and they give me different data. And every such path, it will have a specific type. It could be optional, required, and it could be like an integer. It could be some data structure. So what macros allowed me to do is I have a small crate which has like a database of all the fields, and I can resolve the paths there and actually generate the structure that you see on the bottom with the proper documentation strings and kind of the static fields. I can also generate the code that handles the server responses. So it will deal with all the complexity of this dynamic response, and will give you a proper structure type that you can work with in your Rust program. So it's something like really useful. And even the Rust analyzer, kind of when I hover even within the macro, say on top of overall status or connection state, somehow figures out that it's a structure, gives me the context help on these fields and the actual data type. So yeah, that was great for working with the dynamic API. I have two, like the Vim retrievable and Vim updatable, depending on your scenario, whether you want to kind of one-shot pull the data or you want to kind of continuous updates from the server. Yeah, that's my talk. I wanted to thank the organizers kind of for setting up the conference in Paris. It was a great place and yeah, a great conference. Thank you.